Okay, let us today learn the open chain structure and how to convert them in a 5-membered and 6-membered. So if you remember, we had written glucose molecule where the CHO on the top, CH2OH on the bottom. It's a aldohexose. So 1, 2, 3, 4. We are going to draw D-glucose. So D-glucose will have the OH group on the second last carbon on the right hand side, and we have right, left and right. So this is the structure of D-glucose in the open form. When you want to convert this into a ring form, there are two possibilities. Either it can have a 5-membered ring or it can have a 6-membered ring. So if it is going to have a 5-membered ring where this C double bond OH and the first carbon atom, this is second, third, fourth, fifth and sixth, it is going to react with the fourth OH group. And if it is going to be 6-membered ring, it is going to react with the fifth OH group. So let us see how it happens with the 5-membered ring with the fourth OH group. The H of this will go to the oxygen and the carbon bond will be formed with this oxygen. So eventually we'll get 1, 2, 3, 4 and the CH2OH as it is. These are as it is. We have not changed anything. So let us first write down the things which I have not changed. And now this C, the new bond will be formed between this and this carbon atom, where I said this H will go to the oxygen and the carbon will form a bond with this oxygen. When this H goes to this oxygen, there are two possibilities. Either the OH group will be on the right hand side or it will have it on the left hand side. If the newly formed OH group is on the right hand side, we call it as alpha structure. We call this as a alpha structure. And if it is on the left hand side, the newly formed OH group is on the left hand side like this, what we have drawn. This is called as beta structure. So mind it, this is your first carbon atom, which we call it as a anomeric carbon. We call this as a anomeric carbon. Anomeric carbon can have the OH group on the right hand side. We say this is alpha structure. If it is on the left hand side, we call this as a beta structure. Since it is a 5-membered ring, we can also convert this into a regular furan form. If you remember the furan structure, we always draw with the 5-membered ring with the oxygen. Of course, there are two double bonds here. Here we are not going to draw the double bonds because we have the OH group. Now, always this carbon is written here. So 1, every will have 2 valences. So this is your going to be 1. The thumb rule is we have the OH group or any group which is on the right hand side will be written down. So in this case, alpha will have the OH down on carbon number 1, carbon number 2, 3, 4, and this is CHOH, CH2OH. So we'll write down CHOH and CH2OH. So this is your alpha D glucose. And since it is a 5-membered ring, we can also say alpha D glucofuranose. So last SE we replace by the furan, and ose is always the suffix of most of the carbohydrates. If I want to write down the beta structure, it will be exactly the same, except the first carbon atom will have the OH group on the upper side, beta position. Rest all the things are as it is. So this is your beta D glucofuranose. Now let's see how the 6-membered ring is formed. This is what we are going to write down, where the 6-membered ring, where the fifth OH is going to react in the same manner as we saw here. The H will go to the oxygen and the carbon will form a new bond. So in this case also two possibilities. The newly formed anomeric OH could be on the right hand side or the left hand side. So in that case we will have two structures again. This is your top C's, this is CH2OH, no change. And now since the fourth carbon atom there is no change, I'll write down the things as it is which haven't changed, and a new bond with the fifth carbon atom like this. and either you can have the OH group on the right hand side or on the left hand. So this becomes my alpha isomer. I will call this alpha isomer, and this can be my beta isomer, where the OH group on the anomeric carbon is on the left hand side. So this is my beta isomer. The same structure, this was my open chain structure, this is a ring structure in the Fischer form, and now the same structure in the Haworth form, we can write it like this. The protocol is again to write down this oxygen which is here on this side. So this becomes my carbon number 1, 2, 3, 4 and 5. This is the carbon number 1, where the OH group on the right hand side, as per the said protocol, it will be down, up. This is up, down, down, sorry, this was my first carbon, this was second carbon. So H and OH, the OH and H, third carbon, 1, 2, 3, 4, 5 and 6. Fourth is having OH right hand side, so it will come down, up, and here the sixth one will write down the CH2OH. This is my Haworth form. So this structure is in the 6-membered ring with the oxygen. We call that as alpha D gluco, and 6-membered rings are known as pyran. So we'll say pyranose. Every word has a meaning. Alpha means anomeric OH on the right hand side. D means the second last OH is on the right hand side. Gluco is a glucose structure, and pyranose is a 6-membered form. The same way we can write down this structure with the beta, where the first anomeric OH is on the right hand side. Rest all the things are as it is. Now since this is a 6-membered ring, it will have also a chair form. So chair form, we will write it like this. This is the chair, where my carbon number 1 is this. This is my carbon number 1, 2, 3, 4, 5, right? So these are my first 5 carbons. Now this is having the OH down, H up. You know that when I write down the chair form, it will have axial equatorial. So this is pointing upwards, so its axial will go up, the equatorial will come down. The next carbon axial will go down, equatorial will be up. So likewise, I will first write down all the axial equatorial bonds like this. Now this, in the first carbon, the H is up, so H is up, OH is down, OH is down. Here the OH is down, so here axial equatorial doesn't matter. Look at the orientation. OH is down, OH is down, H is up. So likewise, let us write down all the structures. And CH2OH up. So this is my structure of alpha D glucopyranose in the chair form. Okay, similar way we can write down the structure of beta D glucopyranose. So as I said, we first draw all the axial equatorial bonds and then look at the orientation. This is my carbon number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 and 6. Carbon number 1 is having OH up, so we'll write down OH up, H down, OH down, OH down, H up, H down. So H down, OH up, OH down, H up, H down, CH2OH up. This is also my beta D glucopyranose. Now, if you look at both the structures carefully, in both the structures, most of all the OH, except at carbon number 1 in this case, but rest all the OH and CH2OH in both the structures are axial. If I write down this 1 up and 4 down, when 1 up and 4 down, this way the structure is written, These type of structures are known as 1C4, where 1 is up, 4 is down. This is also a chair form where I have 1C4. In 1C4, where 1 is up and 4 is down, 1C4 structures, always all the OH groups are axial, and these structures are very unstable. As you know, bulkier groups, comparatively bulkier groups, are all axial, and these structures will be always unstable. And to have the stability, what happens is, these are, I'll draw only the alpha D glucopyranose. You practice on the beta yourself and see what happens. So I'm drawing here the 1C4 of alpha D glucopyranose structure. And now what happens, just since all the OH group and the CH2OH group, all of them were axial except the carbon number 1 in alpha, it will flip. It will flip. The reverse flip is very less. It will flip, where now the 4 will come down and 1 will come down and 4 will go up, and the structure will look like this, where this is coming down. So this is my 1, so 1 is attached with oxygen on the top. So this is 1, this is 2, 3, 4 and 5. It will get converted into this. Eventually all the axial equatorial, let us draw first. Okay, this is axial equatorial. Now you all know that when the flipping takes place, the axial bond becomes equatorial. So this H was axial, it will become equatorial. So we'll get H here, OH here, H here, OH here. So have a look at the structure. All the bulkier groups are now becoming equatorial. So this, in this case, this is your carbon number 4 and this is your 1. So this structure is known as 4C1. If you try writing the beta structure, you will find all the OH group are equatorial. So like this, all the OH group will be there. So just have a look. The structure would look like this. Rest of all, of course, are the hydrogens. So this is your alpha structure in 4C1. This is your beta structure in 4C1. These are very important. I would suggest you try with other structures also, where instead of D-glucose, we have a D-mannose, D-galactose, D-fructose. So in the exam, anything can come with either the furanose type of structure or the paranose type of structure. Maybe 1C4 or 4C1 will be asked. Now when we say the 1C4 and 4C1, so we have seen all these structures where of course the question comes, which one will be more stable. So when you look at, there are 3-4 different ways of writing the glucose structure. What we have written here, either we have written in the open form or the 5-membered ring or the 6-membered ring, either 1C4, 4C1. Which is more stable? Of course, most of the time the 6-membered rings are more stable. So 6-membered rings are more stable than the 5-membered. So when you compare with these two rings, the 6-membered ring will be, of course, more percentage will be there in comparison with the 5-membered ring. Now when you compare the alpha and beta structure, which is more stable? So to understand the chemistry of alpha structure or beta structure, let's draw them again in the 4C1 structure. 4C1 structure. So if I draw the 4C1 structure, you will find the OH and the OH and the, so since the OH I have drawn down, this becomes my alpha structure, and if I draw the OH up, this becomes my beta structure. Generally we know that alpha structures will be less stable because the OH group is axial Rest all the groups are equatorial, and beta structure is OH groups are all equatorial, so this should have been more stable. This is our expectation that alpha should be more stable than beta, but that is not the case. This is because if you look at the polarity here, this goes up and this OH polarity is down, whereas in this case this oxygen polarity is rated up, this is going to be here, so this is going to be highly polar, so there will be more dipole interaction. This more dipole interaction will make it less stable, and therefore we have alpha less stable than beta. So this is something different what we observe in the normal way, and this is also known as, this is the anomeric OH, could be axial or equatorial, but because of dipole interactions we have the alpha less stable than the beta, and this is what we call as a anomeric effect. Anomeric effect. So there can be a question on the anomeric effect also. There is a anti-lone pair donation hypothesis. That is also another stability point of view one must remember, where if I look at the structure of any alpha position here, then the lone pair of electrons here can have the structure like this. So we will get easily the transdiaxial elimination, giving you the double bond here. The rest of the things I am not drawing, but you will have the double bond, it is possible. But if headed by the structure being the beta, this X is beta, then in that case this type of reactions are not possible. So anti-lone pair donation with alpha, it's more going to take place than the beta. That is again one must remember. Now another important part we will go for, that is protection. We said that the glucose can be present in the form of open chain or the ring form, either in the alpha or beta, either in the 5-membered or 6-membered. So we have lots of structures here. Then it was a question how to trap these structures. So we will go for protection, or also sometimes known as trapping of structures, or trapping of conformation. Let's say trapping of conformation, either in the open formula or in the 5-membered or 6-membered. If you want to trap the glucose in the open chain structure, then use ETSH, that is C2H5SH, that is ethane thiol. We can use in presence of BF3 etherate, that is OR2. So here when you take the open chain, the structure will get locked or trapped in this form, and the rest of the things are as it is. So if you want to trap the molecule in a 6-membered ring, one can use the ethyl thiol or ethane thiol, where it gets trapped in the open chain structure. If you want to trap a 5-membered ring, then generally acetone is used. So suppose I have a 5-membered ring like this, and I have OH, so I will get the 5-membered ring, and in this case we can use the acetone in presence of H plus. So acetone in presence of H plus, these are the diol, 1,2 diols get protected. So these positions are very favorable, as well these positions. So you will get the protection in this form. Okay, now suppose you want to have only the protection of anomeric. You don't want you know that these all structures whatever we have drawn all are reversible. So we can have the 5-member to 6-member, 6-member to open chain, and this all will be continuously there. And this is therefore the technique to trap. If you don't want the ring structure, then you can use the diethyl thiol, so that now the carbon number 1 will be protected with this SET group, and now the O is not there to get cyclized, and therefore it will be in the open form only. Similarly here it will be in the 5-member if you use the acetone, but if you want to just don't want to protect all others, we can always react the first O this O, that is alpha or the anomeric OH. Anomeric OH you can protect by addition of CH3OH. So you will get the CH3OH in presence of H plus. Only the anomeric OH will get protected. I think may not be this. So let's go for the 6-membered. Yeah, 6-membered we can have that. So when you go for a 6-membered ring, we can have the OH here, and only the first anomeric OH will be protected with the CH3OH H plus, and you will not, once this is locked or the trap as OCH3, now this will not reopen to give you the open chain structure. So this way also many people goes for protection chemistry, where the first carbon is locked and now the structure is locked in the first carbon atom. So this OH is not there, and therefore it will not give back to the open chain structure. So this is another way. Now we can have the protection of this 4th OH and the 6th OH. So they are 1:3 with position with respect to each other. This is carbon number 1, 2 and 3. So 1:3 these positions are. So if I draw the chair form of it in the 4C1 structure, so we have already learned what is 4C1 structure, where we have the OMe maybe in the alpha or beta form. The rest of all the OH groups are here, and we have the OH group. So this is my beta or alpha D glucopyranose in the chair form, and it is in the 4C1, where my carbon number 4 is up and carbon number 1 is down. It's in the 4C1 form. Now when you treat this with the C6H5CHO benzaldehyde in presence of acid, these carbon number 4 and 5 and 6. So 4 and 6, they are 1:3 with each other. They will react. So when we look at the benzaldehyde structure like this O, this H and this H will go as water, and you will get another 6-membered ring. Look at the structure carefully and practice well. So other things are as it is. Now look at this will have O, this will have CH2, and this will have O. This was the original structure part where the H and H was there, and now the benzene will come here. So this carbon is going to have the structure like this. So it will form another chair, and now the pH will preferably to be in the equatorial position of this and the F. So this is the protection in the of the diol 1,3 diol. So remember, benzaldehyde is used to protect 1,3 diol, whereas acetone is used to protect 1,2 diol. So these are the very important question. And the this ethane thiol this ethane thiol is used to protect the open chain structure. One can also use, instead of acetone, one can also use the cyclohexanone. So instead of this, if I use the cyclohexanone structure, which is the same as look like acetone, I can get the same protection here only, except I will have the rings here. So we will have the structure which will look like, instead of this acetone we'll have the ring. That's only difference. So one may get a question in the net, also net set examination, where the protections either with the acetone or cyclohexanone is given. You should be able to think of these protection. If the benzaldehyde given, you should think of 1,3 diol, and if the diethyl ethane thiol is given, you should have the protection with the open chain structure. So that's what we call as a trapping experiment.